All right, ladies and gents, we're going to continue our discussion on the cardiovascular system and talk about blood today. So, when we talk about blood in terms of a definition, right? So, it's a specialized connective tissue. But what's really important here in our discussion is that it's a unique fluid to closed circuit systems as opposed to something like the hemolymph that we would have seen back with things like the grasshoppers and stuff, where they're mixing both their tissue fluid and what we might consider blood, their circulatory fluid, is all kind of one thing. Blood is a completely separate fluid and as a result, completely separate tissue from the fluids that are surrounding the actual tissue cells, the actual body cells themselves. So when we look at blood, it's going to consist of several different types of cells that are then suspended in this liquid matrix that we call plasma. And your blood is then circulated by your heart through your cardiovascular system. And really, its biggest purpose is to be this big carrying system. So it's going to get oxygen and nutrients and things like that to your body cells and then take away the waste products. And if we look in terms of its constitution, all right, here's your plasma. Here's that sort of just liquidy portion that makes up just over 50%, so 55% total. We've got things like water, we've got ions in there, you've got some plasmid proteins that are also there as well, including all of the other nutrients and waste products, gases, hormones, things that are carried by your blood as well, will all be in that suspension, or that solution, I should say. When you look at the actual cellular components, that's about 45%, and that's where you get all of these white blood cells, your platelets, as well as your red blood cells. So when we look at the major functions of the blood itself, right, if you go down the list, there's the transport of materials. That's really what we're focused on here. But we're going to talk a little bit about some of these other pieces as well. When we talked about the immune system, all right, that's where those white blood cells come in. So there's your protection from invaders as well as cancer. Platelets are going to play the role in preventing hemorrhage. All right, so we need to be able to clot your blood, so that's there. But it also is really a big part of maintaining your overall homeostasis for your body. We're going to be able to regulate body temperature, pH, fluid levels, which are then connected to your blood pressure, electrolytes, all of that kind of stuff is really sort of regulated through your blood as well. So if we break it down into each constituent piece, let's talk about the plasma itself. So if we look at blood overall, the plasma itself constitutes 55% of your overall blood volume. But if we break that down even further into what just makes up the plasma, an overwhelming portion of it is water. In fact, we're talking 90%, give or take. The rest of it is other solutes, so things like your electrolytes, calcium ions, sodium ions, plasmid proteins, which are going to influence all sorts of things like your pH, your blood pressure, how thick it is, and then you've got lipids in there, you've got antibodies that are part of your immunity, other proteins that are necessary for blood clotting, like the fibrinogen, if you go through that list in the figure there. So lots of stuff hanging out there in the plasma. Your cellular components then are the actual cells themselves. So if we look at red blood cells, you may have come across, or if we give them the more technical term, we call them erythrocytes. If you look at a blood panel, you'll see them come up as RBCs. Those guys, their major job is to transport the oxygen. And when we get to part 2 of these notes, we'll talk a little bit more about how that loading and unloading happens and where the connection back is to things like diffusion. Your white blood cells or your leukocytes or WBCs, these are the ones we talked about with your immune system. And remember that your basophils, neutrophils, lymphocytes, these guys all have special jobs to play in defending your body against disease and cancer. And then you've got your thrombocytes, your platelets, and these guys are those really small little fragmented pieces of cells that really are going to come in along with a bunch of proteins and really help your blood clot. So that's their job. If we dig a little deeper, all right, and talk about your RBCs specifically. They are the most numerous composition of your cellular components of the blood, and they'll account for about 45% of that 45%, if that makes sense. Their major job is to carry oxygen, and in fact, a single hemoglobin protein that is really the vast majority of the RBC composition as a whole. In fact, if you look, it's 95%, give or take. That hemoglobin is that iron-containing protein that's job is to transport oxygen. Each hemoglobin molecule is made of 4 subprotein chains. It's part of a quaternary structure, and it can bind 4 oxygen molecules as a result. Now, in mammals and our mature cells, our mature red blood cells actually lack a nucleus. They'll actually expel it because they need so much space to hang on to all that hemoglobin in order to do their job. They also don't have any mitochondria either, which is sort of interesting. Once again, it's sort of clearing out just space in order to make room for all that hemoglobin so that it can effectively carry out that oxygen that's necessary. When we look in terms of lifespan, your red blood cells can live somewhere on the order of about 3 to 4 months before your body recycles the components and makes you a new set of red blood cells. And that recycling really does happen by your liver and by your spleen. Your white blood cells, right, we talk about them as white or leukocytes, but truly speaking, they're actually colorless cells. We give them white just as a sort of way to distinguish them. And when you look at them under a microscope, you'll usually see their nuclei purple based on the staining that they use. Now, there are 5 types. Not going to necessarily get back into that here, but if you look at the figure, you can see how the nuclei structure really changes from one type to the other. And remember that corresponds back to what their function is. And their major function for most of these, other than your B and T cells, is to be those phagocytotic cells to take care of the bacteria, take care of the debris, or in the case of your lymphocytes, your B cells, more specifically, they're the ones producing those antibodies. Now, these are the only types of cellular blood components that can be found both in your circulatory system, as well as some of these guys can be found outside, hanging out in things like your lymph nodes and in your tissue, just kind of looking and taking care of infections or cancer as need be. And then you've got your platelets, all right? And these guys are the ones, they're really sort of cellular fragments, and the vast majority of what they are containing are these enzymes that are going to be expelled in the purpose of helping you clot. So what they'll do is they'll help take those enzymatic cascades. In fact, if you look at the picture, you can see this is what they're talking about. Okay, and it takes other proteins in your blood, transforms them with the help of those enzymes to actually form that actual thrombus or a blood clot, so that we can block off blood flow, because at this point something has punctured or opened up a hole in that vessel, and so we need to be able to plug it up. All right, the coagulation part is the actual formation of solid clots from the liquid blood. So your blood's actually clotting, actually congealing, becoming more solid to be able to help. And it really is just a bunch of cascading reactions. So what they're showing you here is a relatively simplistic version of what the end all result would be. And if you take a look, it is a positive feedback loop. So long as this thrombin protein is continuing to be in the environment, in the bloodstream, it's going to keep that enzymatic cascade going, and that's going to keep forming that clot until the vessel actually is sealed off, and we sort of return back to our steady state there. And there's really 3 major phases to a blood clot. And you've got the actual vascular phase itself. This is the local contraction of an injured vessel. So if you've ever gotten a nice cut and sort of felt that throbbing, that's what we're talking about as far as that vascular phase. And its job really is just to get all of these cellular components to that injury as fast as possible. You get the platelet phase that comes in next. And here's where you get the actual platelets themselves sticking to those damaged vessels, trying to plug up the clot. And then you get the coagulation phase, which is really those platelets releasing those enzymes to get that cascade to keep going until that plasma actually forms that blood clot itself. So all the other components are there, and we actually get the coagulation and the blood clot to form. Now, if we're talking blood cells, let's sort of just take this a step back and kind of talk about where they come from. So when we look at the formation of blood cells in your body, all of them start off as stem cells in your bone marrow, all right? And they will go through this process known as hemopoiesis, or the production of formed elements. And those stem cells are really starting this production during fetal development. Somewhere between the 2nd and 5th month of development, those fetuses will start actually producing their own blood cells. When we're looking at them at that point in time, most of the hemopoiesis is taking place mainly in your liver and your spleen, and they're really taking care mostly of red blood cells initially, and then the white blood cells will follow. After that 5th month, there's enough of the bone growth and bone development that is then finally set up and in place in that fetus to actually take over the production. And if you look, you've got these sort of completely blank stem cells that will then sort of work themselves into what we would typically talk about as something like an adult stem cell, where they're starting down a path. You get your myeloid stem cells that can become these guys, so your red blood cells, a handful of white blood cells, the platelets, and then your lymphoid stem cells, which become your B or T cells. Remember, B cells will stay in the bone marrow and mature there. T cells will end up at your thymus and go finish their maturation stage there. And eventually we've got to replace all of this, right? So your cellular elements will wear out over time. We talked about your red blood cells being somewhere, a few months before we have to replace them. The white blood cells really kind of depends on how much of an infection you're dealing with or cancers you might be dealing with. Platelets, a similar idea, how much are you using? But they all come from a common source of stem cells in your red bone marrow, which is specifically the bone marrow that we'll find in things like your ribs or your vertebrae. Same thing in your sternum and your pelvis. So if you've ever heard of somebody who's gotten a stem cell transplant for leukemia, leukemia is a cancer of the blood, and so they'll typically take those stem cells out of someone's pelvic bone. Big bone, it's easy to get a hold of as opposed to something like your ribs or your sternum, so they can harvest a lot of it. But it's not fun. They're drilling into your pelvis to be able to get those guys. But if the replacement works, it can be an effective way to treat that type of cancer. So your lymphocytes, right? These are the ones that come from those lymphoid stem cells. Your myeloid stem cells are the ones that will eventually become the vast majority of your white blood cells, platelets, as well as your red blood cells. And there are actually hormones specifically connected to the stimulation of your red blood cell production. So if your body is sort of out of whack and we need to increase the oxygen delivery system, your body can produce this hormone called erythropoietin, or EPO for short, and that's going to stimulate your bone marrow to then produce more myeloid stem cells to then produce more erythrocytes. If your oxygen delivery system is kind of at a minimum and we need to bolster that, your body can kind of work through a feedback mechanism and make that happen.